We are done with series and parallel combination of resistors, and now we are going to have discussion on series and parallel combination of capacitors. And after understanding the basics of series combination and the basics of parallel combination in the previous lecture, it won't be difficult to understand the series combination of capacitors and the parallel combination of capacitors. So let us begin our discussion with series combination of capacitors, and for this I have taken this particular circuit in which two capacitors are connected back to back, and there is one voltage source providing the voltage V, and the capacitance of the first capacitor is equal to C1 and the capacitance of the second capacitor is equal to C2, and this plate of the first capacitor is connected to the positive terminal of the source, and therefore the plate will have the positive charge and this plate will then have the negative charge. And let's say the charge delivered by the source is equal to Q, so this plate will have the plus Q charge and this plate will have the minus Q charge. Now when you focus on the second capacitor, you will find this plate is connected to the negative terminal of the source, and therefore it will have the negative charge, and due to this reason this plate will have the positive charge, and the amount of charge delivered by the source will be equal to Q. Therefore this plate will have minus Q charge and this plate will have the plus Q charge. So you can see that in series combination all the capacitors are getting the same charge. Now we will calculate the equivalent capacitance, that is, we want to have a single capacitor in place of these two capacitors, and we want to calculate the capacitance of this capacitor, and for this we will apply KVL in this loop, and let's say voltage across first capacitor is equal to V1 and the polarity will be plus minus, and the voltage across the second capacitor is equal to V2 with plus minus as the polarity, and when we apply KVL we will have plus V, then we have minus V1, after this we have minus V2 equal to 0. From here we can say that V is equal to V1 plus V2, and we know Q is equal to CV, and from here we can say that V is equal to Q over C. Now talking about the first capacitor, voltage is V1, capacitance is C1 and Q is the charge. So we have V1 equal to Q over C1. Now moving on to the second capacitor, you can see that the voltage is V2, the capacitance is C2 and the charge is Q. Therefore voltage V2 is equal to Q over C2. Now for the equivalent capacitor, we have V as the voltage, C equivalent as the capacitance and Q as the charge. Therefore voltage V is equal to Q over C equivalent. Now we will put V1, V2 and V in this equation, and we will have Q over C equivalent equal to Q over C1 plus Q over C2, and from here we are getting 1 over C equivalent equal to 1 over C1 plus 1 over C2. So remember this result, and from here you can calculate the equivalent capacitance. It will be equal to C1 multiplied to C2 divided by C1 plus C2. So the formula we are getting for series combination of capacitors is something similar to the formula we had for the parallel combination of resistors. Now when we have n number of capacitors connected in series, let's say C1, C2 all the way to Cn are the n capacitors connected in series, then the equivalent capacitance can be calculated like this: 1 over C equivalent equal to 1 over C1 plus 1 over C2 plus all the way to 1 over Cn. Now when C1, C2, C3 up to Cn all are same and are equal to C, when all the n capacitors are having the same capacitance values and they are equal to C, then the equivalent capacitance can be calculated like this: 1 over C equivalent equal to 1 over C plus 1 over C all the way to 1 over C, which is our nth term. And from here we will have 1 over C equivalent equal to n times 1 over C, or we can say C equivalent is equal to C over n. Now from here it is clear that the overall capacitance or the equivalent capacitance will reduce when we connect the capacitors in series. For example, we have C equal to 2 microfarad and we are connecting 3 capacitors in series, then the equivalent capacitance will be equal to 2 divided by 3 because n is equal to 3. So compared to 2 microfarad, 2 over 3 microfarad is less. So the capacitance reduces when we have series combination of capacitors. Now we will move on to the parallel combination of capacitors. Let's say this particular point of the circuit is connected to the ground. This means potential here is equal to 0 volt. And when potential at this point is equal to 0 volt, potential here will be equal to 0 volt, and here also potential will be 0 volt, and here the potential will be V volts. Therefore here also the potential will be V volts, and here also the potential will be V volts. So you can see that the potential difference across the first capacitor is V minus 0, that is V, and the potential difference across the second capacitor is V minus 0, that is V. So the potential difference or the voltage across both the capacitors is same, and this is what happens in parallel combination. Now let's say Q is the charge provided by the voltage source and Q1 is the charge provided to the first capacitor by the source, and therefore plus Q1 is the charge at this plate and minus Q1 is the charge at this plate, and the charge provided to the second capacitor is equal to Q2. So we have plus Q2 charge at this plate and minus Q2 charge at this plate. So the total charge is equal to Q, and Q1 is the charge provided to the first capacitor and Q2 is the charge provided to the second capacitor. So the sum Q1 plus Q2 will be equal to Q, and from here we can see that Q is equal to CV, and therefore Q1 will be equal to C1V. C1 is the capacitance of the first capacitor and voltage across the first capacitor is V. So Q1 is equal to C1V, and for second capacitor Q2 is equal to C2V, and if we have one equivalent capacitor in place of these two capacitors, then Q will be equal to C equivalent V. Now we will put Q1, Q2 and Q in this equation, and we will have C equivalent multiplied to V equal to C1 multiplied to V plus C2 multiplied to V. From here we will have C equivalent equal to C1 plus C2. So remember this result. Whenever the capacitors are connected in parallel, then their capacitances are added, and the formula is same as the formula we had in series combination of resistors. Now when we have n number of capacitors connected in parallel, then the equivalent capacitance will be equal to C1 plus C2 all the way to Cn. And if C1, C2 all the way to Cn are same and are equal to C, then the equivalent capacitance will be equal to n times C. Now from here it is clear that when capacitors are connected in parallel, the overall capacitance increases. For example, let's say n is equal to 3, that is 3 capacitors are connected in parallel, and C, that is the value of capacitance of the one capacitor, is equal to 2 microfarad. Then when 3 such capacitors are connected in parallel, the equivalent capacitance will be equal to 3 times 2, that is 6 microfarad. So compared to 2 microfarad, 6 microfarad is more. Therefore, capacitance will increase when capacitors are connected in parallel. So I hope this lecture was clear to you. Now I will end it here. See you in the next one.